Foundational AI research exists as a chaotic landscape of raw data. The volume of academic text and mathematical formulas makes identifying a clear path impossible. To navigate this, Ilya Sutskever, a central figure in the development of deep learning, curated a list of the top 30 papers he considers essential. Sutskever shared this selection with John Carmack, framing the list as a definitive curriculum. He argued that truly learning these 30 papers would account for 90% of what matters in the field today. Within that list, 4 specific papers trace a direct evolutionary lineage of sequence modeling: understanding LSTMs, neural machine translation, attention is all you need, and scaling laws. These works document a targeted mathematical war against a single technical obstacle, the fixed-length bottleneck. The history of modern AI is the systematic dismantling of this exact limitation to enable massive parallel scaling. We begin with Andrei Karpathy's baseline premise. Recurrent neural networks, or RNNs, are effective because they process sequential data by maintaining a recurrent hidden state. The network updates this state iteratively. It takes an input vector, merges it with the existing hidden state, and carries the result forward to the next step in the sequence. However, this continuous multiplication causes a mathematical dilution known as the vanishing gradient problem. The network loses a signal from the earliest inputs before it ever reaches the end of the sequence. Christopher Ola's analysis of long short-term memory networks describes the first architectural solution to this memory loss. The innovation of the LSTM is the cell state. This acts as an informational conveyor belt, a straight, uninterrupted horizontal line that allows data to bypass the main recurrent layer. A forget gate manages this belt through pointwise multiplication. It uses a sigmoid layer to decide exactly which data should be dropped from the state. Simultaneously, an input gate uses pointwise addition to push new, relevant information into the conveyor belt. But even with a perfect memory belt, a second bottleneck remained. The entire input sequence still had to be compressed into a single vector before the decoder could generate a result. Compressing a 1,000-word document into a single, fixed-length context vector causes a loss of resolution. The network cannot represent that much complexity in a single point. LSTMs fixed how networks remember, but they did not fix how they compress. The fixed-length bottleneck was still in place. The 2014 Neural Machine Translation paper by Bodenau and colleagues broke the fixed-length standard. Their architecture pivoted the encoder. Instead of a single point, it outputted a continuous sequence of multiple distinct annotation vectors. This enables attention. For every target word, the decoder computes a similarity score over all source vectors, represented by lines of varying thickness. The context is now dynamic. As the decoder moves through the sequence, it recalculates these weights and shifts its focus to the specific part of the source data it needs. This dynamic alignment allows the network to maintain resolution regardless of the sequence length. We solved compression, but the process was still bound by recurrence. Sequential processing is inefficient on modern hardware. You cannot compute step 100 until step 99 is complete. To reach a meaningful scale, the field needed an architecture that could process entire sequences in parallel. The 2017 paper, Attention is All You Need, provided that shift by discarding the RNN entirely. In self-attention, every input vector is simultaneously projected into 3 distinct representations: queries, keys, and values. The formula for this operation is the scaled dot product attention. By multiplying the query matrix by the transposed key matrix, the network computes the attention weights for all tokens at once. After scaling and applying a softmax for probability, the result is multiplied by the value matrix to produce the final output vectors in parallel. This architecture effectively changes the path length of information. In an RNN, the path length is linear, or O of n. Information must travel through n steps to connect 2 distant points in a sentence. In a transformer, that path length is constant, O of 1. Matrix multiplication connects every token to every other token instantly, regardless of distance. Without recurrence, these calculations can be sharded across thousands of GPU cores at the same time. The Swannies architecture reduced sequential time into parallel geometry, providing the necessary framework for a massive expansion in scale. Parallelization research, like GPipe, confirmed that transformers can be sharded across massive supercomputers efficiently. This hardware efficiency leads directly to Jared Kaplan's research on scaling laws. His findings suggest that once the recurrence and the fixed-length bottleneck were removed, model performance became highly predictable. On this log-log chart, as model size increases on the x-axis, test loss drops predictably. It follows a power law relationship across multiple orders of magnitude. When we shift the x-axis to compute, the same linear trend appears. Performance scales efficiently against raw floating-point operations. We also see a spike in sample efficiency. Larger models learn faster, requiring less data to reach the same performance milestones as smaller networks. Sutskever's top 30 list provides the roadmap for how these core architectures shifted artificial intelligence from an empirical art into an exact industrial science constrained only by the laws of physics and compute.